Several years ago, we made a short video called 35, the magic number, and it's now time to improve on that and to add a second magic number. These numbers will help you to calculate voltage drop and loop impedance, or ZS, without the need to refer to tables, and they are quick and accurate. There are always frequent questions on this, so it obviously matters to many of us. Questions like, I've heard that 35 is a magic number. Magic for what? Or, very recently, I've been told that the number 35 can be used to find ZS. How does that work? Then we had, can we have more detail please about how the ZS numbers are actually worked out? And 44 is also a magic number that I personally use quite frequently. Let's begin this with the number 44. What is it used for? How do we use it? We use this to help us when we make voltage drop calculations. This way, there's no need to keep referring to tables of millivolts drop. Just the number 44 is all that you need to get started. This is the standard voltage drop formula, and we have other videos on this going into very great detail. We've shown here what each of the symbols means as a reminder. We need to know how many millivolts a certain size of cable will lose per amp of current flowing through it for every meter length of the circuit. Then the design current. This is how many amps the circuit or equipment will consume when switched on, and the length is the meters from end to end of the circuit. When working on site, it's easy to work out the design current, or use the breaker ratings as a last resort, and the length is easy to pace out. But to find the MVAM number, we need a set of tables. Or do we? What do we do on site when you've no books with you? And it happens. Let's go back to basics and look at one of these tables. In this case, for flat profile PVC twin and earth cable. This is table 4D5 on page 456 of the regulations book, the Brown Amendment 2 book. In the leftmost column, we have the sizes or cross-sectional areas of the phase and neutral wires. We're not interested in the earth or CPC for voltage drop calculations. Starting with 1mm cable on the left, if we scan across to the rightmost column, we have the number 44. That is the MVAM number for 1mm copper conductor. If we look down the left column and find 2.5mm cable, and then look in the right column, we have an MVAM number of 18. 2.5mm twin and earth cable will drop 18 millivolts for every amp that flows through every meter of cable. More amps, more volts drop. Longer lengths, more volts drop. If we put the cable sizes and the millivolt numbers into a simple graph, we get something like this. If we find 1mm conductor on the bottom, the horizontal axis, and make a line vertically straight up to the red line, we find that they will intercept at a value of 44 millivolts per amp per meter, as shown on the left. This is easy because 44 divided by 1 is still 44, but that's our answer so far. Now travel along the bottom axis and find 10mm cable this time, up to the red line and then horizontally back to the left of the graph. This will give us 4.4 millivolts, and 44 divided by 10 is 4.4 millivolts per amp per meter, and this same relationship will work for all sizes of twin and earth cable up to 16mm cable. So it really is very simple. 44 divided by the cross-sectional area will give the MVAM number to use in the voltage drop calculation. If you can remember the calculation and you can remember 44, who needs the books? This is called a linear relationship, and the table shown here compares each cable size to the MVAM numbers that both the regs book and the on-site guide give, and what the numbers are when calculated by dividing 44 by the cable CSA. There are very small differences in the calculations, but the calculations we've just done are the most accurate, as the regs book and the on-site guide will round up or down to make things look tidy. And to be honest, the actual differences in the end results are not worth worrying about. Let's move on to ZS now, sometimes called loop impedance and more properly earth fault loop impedance, and this is measured between the phase and CPC wires. This will use the magic number 35 and works for ZS for BS-EN 60898 circuit breakers and BS-EN 61009 RCBOs. We are going to work our way through the book properly and follow each of the steps to finding the ZS values by using the book. Hopefully, by doing it this way, you will understand where we get the numbers from that make up ZS. There are two types of ZS values that we will come across. First are the tabulated values, as given in the tables of the wiring regulations. These are the values that often appear in 18th edition exam questions. Then the measured values that we compare our on-site test results against, often called the 80% values or the 80% rule. There are several methods to find the measured ZS values. To calculate a measured value, we must first calculate the tabulated value. Or we can look in the appropriate tables in the on-site guide, or we can use the magic number 35 if we have no books or tables, and this is so easy, it's a winner. For us, it all begins with page 417 of the Wiring Regulations book and figure 3A4, which is specific to Type B circuit breakers and RCBOs. Ignore all the complicated looking lines, we just need the table at the top right. This is that same table enlarged. The left column of the table lists the different circuit breaker sizes. These are the IN numbers, the nominal current rating of the device, the numbers shown on the front of the breaker. The word nominal just means the name that you call the device. This is what you will ask for when you go to the wholesaler. A 6 amp breaker please, a B32 breaker please, and so on. The right hand column is IA. This is the current causing operation of the device within the time stated in part 4 of the wiring regulations. It's the amount of current that will trip the breaker in 0.4 seconds or less. Don't get these two confused. IN and IA are totally different. Look at the 6 amp device first. It has an IN or nominal value of 6 amps. That's what we call it, a 6 amp breaker. And it has an IA of 30 amps. So, if we can design the circuit so that at least 30 amps flows during a fault, the device would trip in 0.4 seconds or less. A 32 amp breaker has an IN of 32 amps and an IA of 160 amps. And you will see shortly that bigger circuit breaker sizes mean smaller permitted ZS values. We will follow the story of a 6 amp circuit breaker and calculate the measured ZS by doing the whole thing. We begin with this table on page 417 and find that a 6 amp type B breaker needs 30 amps of fault current. The nominal voltage that we use is always 230 volts for calculations. So 230 divided by 30 is 7.67. The first stage is done, 7.67 ohms. Now we should go to page 68 for the next bit. On page 68 we have table 41.3, specific to circuit breakers and RCBOs. The section for Type B devices is shown at the top of the table. But before we go any further, we must look at note 1 just below the table. It tells us to use a C-min factor of 0.95 on the number that we've just calculated. So far, we've divided 230 by 30 to get 7.67 ohms. Now, we must multiply 7.67 by 0.95 to get another number, 7.28 ohms in this case. This is ZS tabulated, where tabulated means that it is shown in the tables in the wiring regulations book. A C min factor, C minimum, is a factor that is used to allow for voltage fluctuations in the network where voltages may drop to 220 volts or less. It will make ZS smaller, more critical. And that is the second stage completed. ZS tabulated is 7.28 ohms as shown in the tables. But we're not finished yet. We still need to find the maximum permitted measured ZS for our test meters. We will change the tabulated ZS into a measured ZS by multiplying the 7.28 ohms by 0.8. This is sometimes called the 80% rule, and more information is shown on page 410 of the regulations book. 0.8 is an adjustment to allow for temperature increases in the cable. 7.28 multiplied by 0.8 is 5.83 ohms, and this is the maximum permitted measured ZS. This is what we will compare our on-site test results against. If our test meter reading is less than 5.83 ohms, then that is a pass for a 6 amp Type B breaker. If you look at table B6 in the on-site guide, the ZS is shown as 5.87 ohms. This is a typo. The correct ZS should be 5.83, but the difference is so small it will make no difference to many on-site test results. You'll find a formula for the whole thing on page 410 of the Amendment 2 Wiring Regs book, and this is shown below. But to use the formula, we will still need to begin on page 417 to find the amps value of IA. We've used the formula from page 410 to calculate the maximum permitted measured ZS of the same 6 amp Type B circuit breaker, and the result is the same 5.83 ohms. But we could save ourselves a lot of calculator time by just dividing the magic number, which is 35, by the nominal rating of the circuit breaker, in this case 6 amps. 35 divided by 6 is 5.83 ohms, depending how you round up or down the decimal places. So much easier. We've just done in a few seconds what the long way round has taken several pages and many minutes to calculate. And it works for all BS EN 60898 breakers and 61009 RCBOs. This is a 20 amp Type B breaker. Start the clock. 35 divided by 20 is 1.75 ohms. Stop the clock. That took me 4 seconds, and the answer, we know, is correct. And most importantly, no flicking through books is needed. Now try it with a 32 amp Type B breaker. 35 divided by 32 gives the maximum permitted measured ZS of 1.09 ohms. Depending on how you round up or down, some books show this as 1.09 ohms, others as 1.1 ohms. It matters not, it's the same, but if your circuit is that close to the limit, you need to be looking at ways of reducing the actual ZS. Now we can ask another popular question. How can we change Type B to Type C or even to Type D? Very easily. Let's use a 10 amp circuit breaker this time. Calculate the measured ZS using 35 divided by 10. This is 3.5 ohms for a Type B device. For a 10 amp Type C breaker, just divide the Type B answer by 2. So a 10 amp Type C will be 3.5 ohms divided by 2, which is 1.75 ohms. And to find the maximum ZS for a 10 amp Type D, divide the Type C answer by 2 again, and we have 1.75 divided by 2, which is 0.87 ohms. Job done, and you can check the answers in table B6 of the on-site guide on page 145. So easy to do. Remember that for this calculation we are using IN, the nominal current rating of the breaker, the number that is printed on the breaker. And just a reminder of those magic numbers, use 44 divided by the CSA of the cable to find the MVAM number to use in the voltage drop formula, and 35 divided by the nominal current rating IN will give you the maximum permitted measured ZS for Type B circuit breakers. Thank you for watching, it really is appreciated, and we hope that you found this video useful and informative. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And you will find even more information, videos and help on our website at learnelectrics.com. And don't forget that you can also type in Learn Electrics, all one word, into the YouTube search bar to go directly to our channel at any time from any computer. We are constantly adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.